Next up is exercise 8 from May 2018, which is a question about the Backlund transform. So we have these two equations here that express Vx and Vt in terms of V and U. And in part A, you want to show that these relations give a Backlund transform between Berger's equation for U, which is written here, and the heat equation for V. So, okay, let's first try to find the equation for V, which seems simpler. So that's part A. So to find the equation for V, we can use the first equation here. Let me call these two equations 1 and 2. Let's use equation 1 to solve for U. If I rearrange, I get that U is minus 2 Vx over V, which is also minus 2, the derivative with respect to x of the logarithm of V. And now we can substitute this in equation 2. So we get Vt is equal to 1/4 of U squared. So that's 4 Vx squared over V squared minus 2 derivative of U with respect to x. So let's write this as plus 4 Vx over V differentiated with respect to x. And that multiplies V. Okay, so now I'll compute the derivatives. I no longer use expressions up there. I can simplify the factors of 4. So I get Vx squared over V squared from the first term. And then the second term, first I differentiate the numerator, I get plus Vxx over V. And then I differentiate the denominator and get minus Vx over V squared times the derivative of V with respect to x, which is again Vx, and this all multiplies V. So now the first term and the third term nicely cancel out, and we get that this is equal to Vxx. So the equation for V is Vt equal to Vxx, which is precisely the heat equation that we wanted to find. So Vt equal Vxx heat equation. Okay, so next we want to find the equations for U, which is a little more complicated. It involves 3 terms, and that's Berger's equation. So to get the equations for U, what we'll do is the standard trick that we use in the Backlund transform. So we'll cross differentiate. So we'll differentiate equation 1 with respect to 2 and equation 2 with respect to x. So we get 2 expressions for the mixed derivative of V with respect to x and t, and then we will compare. And hopefully, perhaps by using some of the other equations further, we will be able to eliminate V. So to find the equation for U, we cross differentiate. So let's first compute derivative of equation 1 with respect to t. Let's first compute the derivative with respect to t of equation 1. So that's Vxt is equal to minus half UTV plus UVT. And then we can use equation 2 to plug in an expression for Vt. So we'll get minus half Ut, and then I will factor out V plus U times Vt, but Vt is given by expression 2, so we get plus 1/4 U u squared minus 2ux, which all multiplies v. So let's bring v to the left-hand side. So we can rewrite this as minus 2 vxt over v is equal to ut plus 1/4 u times u squared minus 2ux. Okay, so now we do the same for equation 2. We differentiate equation 2 with respect to x. So we get vtx, which is the same as vxt, because we assume that equations, that functions u and v are sufficiently differentiable. So I'll have to differentiate the right-hand side of equation 2 with respect to x. So I get 1/4. Let's first differentiate v. So I'll get 1/4 u squared minus 2ux times vx. And then I differentiate the bracket. So I'll get plus 1/4 to ux minus 2uxx, which multiplies v. So next, I can use equation 1 to express vx in terms of u and v. And so we get minus 1/8 u squared minus 2ux times v from the first term. And the second term is plus 1/2 ux minus uxx times v. So now again, I can bring v to the left-hand side, and so I get minus 2 vtx over v is equal to, I multiplied by minus 2 so that I can compare with the expression above. So I get 1/4 u squared minus 2ux from the first term, and the second term I need a minus sign, so I'll write plus uxx minus ux. Okay, so now I will compare the two equations that I call star and double star. So the left-hand sides are the same, so compare. So star is equal to double star. And so the right-hand sides have to be the same, and I get ut plus 1/4 u squared minus 2ux must be equal to 1/4 u squared minus 2ux plus uxx minus ux. So now I can simplify the terms which involve 1/4 u times the bracket, and what we're left with is an equation for u, which hopefully is precisely Burger's equation. So let's check. We want to find that ut plus ux minus uxx is 0, and this is precisely the equation that we have found. Okay, so next we look at part B. So in part B, we're given a solution of Burger's equation, u of x and t equals 2 times c, where c is a constant. And we want to apply the Backlund transform to find the corresponding solution v of the heat equation. So what we need to do is to plug u equal to c, where c is a constant, in the Backlund transform equations 1 and 2. So we'll get the system of two equations. So the first one is Vx equals minus 1/2 u times v, so that's minus c times v. And the second equation is Vt equals 1/4 times u squared, that's 4c squared. And we get minus 2 ux, but u is equal to a constant, so the derivative is 0, And so we get 1/4 times 4c squared. So that's c squared times v. So that's the system that we want to solve. So now we can integrate. So the first equation is an ordinary differential equation with respect to the variable x, where t is a spectator. So the solution of this is that v is exponential of minus c times x times an integration constant, which is actually a function of t, the spectator variable. Let me call it f of t. So similarly, for the second equation, is an ordinary differential equation with respect to the variable t. The other variable x is a spectator, so we can integrate. So v is going to be proportional to exponential of c squared t times an integration constant, which is actually a function of the spectator variable x. So let me call it g of x. Okay, so now we can compare the two expressions for v. And we see that f of t, integration constant, or rather function in the first expression, must be proportional to exponential of c squared t, where the proportionality factor is a constant a. And similarly, we can determine that g of x must be equal to exponential of minus cx times an integration constant. In principle, we could call it b, but that has to be equal to a, so that the two expressions agree. And so we find that v is equal to an integration constant a times e to the minus cx times e to the c squared t, or equivalently, that's equal to a times exponential of minus c times x minus ct. So this is a solution of the heat equation. And if you wanted, we could check that indeed the expression for v that we found solves the heat equation Vt equal V xx, which is easy to do. Finally, in part C, we want to find, so we're given a special solution of the heat equation for V that is given here, this exponential factor with 1 over square root of t in front. So we don't need to check that this is a solution of the heat equation. We're even told that it can be obtained by time evolution of Dirac delta function at t equals 0. If you want to check that, that's a nice exercise. But let's take this at face value. So we're given this solution T of the heat equation and want to apply now the Backlund transform to find the corresponding solution of the Burger's equation. And finally, we want to determine whether this solution that we find is regular or singular. So let's do that. So again, we need to plug this expression in the Backlund transform. So now we want to plug V equal to 1 over square root of 4 pi t exponential of minus x squared over 4t in the Backlund transform. But we noted earlier that the first equation in the Backlund transform, equation 1, can be used to determine u. So we just need to plug it in equation 1. So equation 1 tells us that u is minus 2 vx over v, or equivalent to minus 2, the derivative with respect to x of the logarithm of v. So when we take the logarithm of v, there are two terms. One is a logarithm of 1 over square root of 4 pi t, which is x independent. And the second term is the logarithm of the exponential where x appears. So we get minus 2 times minus x squared over 4t differentiated with respect to x. So when we differentiate x squared with respect to x, we get 2x. So all in all, we get x over t. So this is the solution of Berger's equation that we were after, and next we'll ask whether this solution of Berger's equation is regular or singular. And here the answer is that the solution is singular because it diverges for t equals 0.